SwayamPrabha. Digital India. Educated India.
In this lecture, we continue our discussion on generation of forces and moments, and we look at the non-dimensional coefficients that we discussed in the last lecture. Additionally, we are going to look at the shape of an aircraft and its different control surfaces. As I mentioned, we will revisit the non-dimensional coefficients. We will have a relook at lift and drag forces and their dependence on angle of attack, thrust, how thrust is generated by an aircraft, external shape and surfaces of an aircraft, and the force and moments which it can generate. These are the key points of this lecture. Let us continue our discussion on the non-dimensional coefficients. So, last time we had stopped here. So, you recall that there were 3D bodies and 2D bodies, and for the 3D bodies we used the uppercase nomenclature. Now, for a 2D body we will use lowercase for lift coefficient, and the force is basically the lift per unit span. It is divided by q infinity by c. Remember that the reference area in this case S is the chord into unit span. The chord essentially remains constant in the third direction. So, what comes out of it, the c is basically representing area. Therefore, these are dimensionally consistent with the numerator, both are forces. This is essentially pressure, which means force per unit area, and this is area. So, the two when multiplied gives you force. Similarly, the drag would be the drag per unit span by q infinity c. The pitching moment will be moment per unit span by q infinity c square. So, it is c times c. The additional c is taking care of non-dimensionalizing the moment. To recall again that 2D bodies have infinite span, and they do not have any variation in cross sectional geometry along the span, while 3D bodies have finite span. You will later see that we will discuss in more detail the aerodynamic characteristics of airfoils, which fall in the 2D category, and finite wings, which fall in the 3D category. Last time we had derived the expressions for the forces and moments by considering lengths SU and SL on the upper and lower surfaces. That may not always be the most convenient way of doing things. So, this time we are going to use the lengths x and y while expressing the coefficients for normal, axial and forces and the moment. Before we do that, we incorporate another two coefficients into our list, the pressure coefficient Cp which is the difference between the local pressure and the free stream static pressure P infinity. So, the P infinity is the static pressure which exists far upstream of the airfoil, and the skin friction coefficient So, these are the two additional coefficients apart from the force and moment coefficients which we are introducing. As I was saying you, instead of SU and SL, this time we are going to take a different means by which we represent the forces by bringing in the dx and dy instead of ds. So, if ds is a directed element, this is its inclination, we can have the corresponding dx and dy's which can represent it. So, dx will be ds cos theta, dy would be minus ds sin theta, and of course, S is C into 1, which we already discussed for 2D bodies. Using these nomenclatures, we can now write the normal force coefficient like this, which is a very convenient form. So, you see pressure coefficients are now coming into the picture, which we have defined here for the upper and lower surfaces, and skin friction coefficients are coming into the picture associated with the local slopes. So, this gives the total contribution of pressure and skin friction to give you the normal force coefficient. In a similar manner, you can write an expression for axial force coefficient. As long as you have details of the geometry, the dy dx values can be computed at each and every point, and thereby you can numerically integrate these expressions. As we recall, there is a 1 by c square for moment, an additional c to maintain non-dimensionalized values. There should be a bracket here with a YL outside. Let me erase that part. This is the complete expression for the moment. Remember that the YU should always be taken as positive, which is above the chord. YL should always be taken as negative because it is below the chord. dy dx, whether for upper or lower surface, is positive for positive slopes of the surface and negative for negative slopes. And once you are done with calculation of Ca and Cn, obviously you can write down expressions for Cl and Cd by using the angle of attack. So, this is how the force and moment coefficients can be worked out more conveniently by using the x, y coordinates of different points on the surface of the body, which is more convenient by using the running coordinates S u and S l. So, that was a little more discussion on the non-dimensional coefficients. We are now having a brief look at this picture, which we have seen in an earlier lecture, where we started discussing about the different forces which act on an aircraft in steady level flight. So, we already spent quite some time on lift, weight, little bit on drag, and we are yet to discuss more on drag and thrust. And remember that in steady level flight, these forces are acting through the center of gravity. Let us have a little more look at the drag. Now, aerodynamic drag has different sources. So, when we say drag, it is not the skin friction drag alone, though we have pinpointed on the skin friction drag, because that is one of the most primary components. Now, skin friction drag is produced, as we know, by all the exposed surfaces of the aircraft due to the surface shear stress distribution. Pressure drag is produced due to imbalance of pressure between frontal and rear portions of the different surfaces of the aircraft, which means, let me give an example to show you. For example, if you have a body like this and it is facing a flow which is impinging on it, and you find that this happens to be an axis of symmetry of the body. If you look at the pressure distribution on the front half of the body and you look at what it is in the rear part of the body, if the pressure distributions are identical, then there is no drag, the drag is 0 as far as the pressure drag is concerned. So, this we are saying based on the pressure distribution on the body. The pressure distribution, if it is symmetric about this vertical axis of symmetry of the body, then it ends up producing no drag from the pressure side. However, if there is an imbalance, there would be a pressure drag created. Irrespective of the pressure drag, the skin friction drag remains as long as the nature of the flow is viscous. We will talk about some flows which nearly behave like inviscid or lacking viscosity later on in the course. Under such conditions, you can neglect skin friction drag. A variant of pressure drag is felt by finite wings, and that is called as induced drag. We will learn this later when we discuss about finite wings. Additionally, on high speed aircrafts and rockets, significant drag may be produced, but the route to such drag is very different. It is due to the presence of shock waves and expansion fans, and that is called as wave drag, and that is going to occur only when the flow goes supersonic or still faster. When we are calculating drag produced by the wing of an aircraft, then how would we express the drag force? We will say that it has a drag coefficient which can be multiplied by the dynamic pressure half rho v square times the wing area in order to give us the drag force, which basically means that the drag force is proportional to the wing surface area and with the square of the velocity. So, this relationship is somewhat similar to the lift force represented in terms of CL, which we discussed earlier. Like lift, the drag coefficient is also often determined experimentally, and it is a function of the shape of the body, the flow velocity, especially the Reynolds number, Mach number, etc., representing the flow. So, depending on that, the drag coefficient would vary. It needs to be determined experimentally. We are revisiting some of these pictures which we saw earlier, which come from a numerical simulation. We have an airfoil section a 2D section basically, and you have the flow solved by solving a set of partial differential equations which we call as Navier-Stokes equations. And we find that as we look from top to the bottom, we are looking at higher angles of attack. So, at a comparatively lower angle of attack, most of the flow seems to be following the body. Only a small portion towards the trailing edge seem to be developing some features which indicate that the flow is no longer completely following the body surface. So, if it does follow the body surface, we see an attached flow. If it does not, then what we have is a separated flow. We will learn more about this later, but it is good to get introduced to these terms early in the course. Attached flow and separated flow. You are largely seeing an attached flow here, and you are seeing a largely separated flow over here. There are flow structures which are developing, especially you will notice they are developing on the upper side of the airfoil and its neighborhood, not on the lower side. The lower side is often called as the windward side. It seems to be facing the wind more head on, while the upper side seems to be kind of shadowed. It is not seeing the wind head on. Upper side is often called as leeward side. When the flow becomes very disorganized and it is not following the upper surface, there will be a loss of lift. We say that the flow is stalled, and there would be dramatic increase in the drag as well. So, when lift decreases and drag increases, the L by D ratio, the lift to drag ratio, which indicates aerodynamic efficiency, is highly compromised. So, when the flow starts separating, when it no longer follows the airfoil surface, there is a dramatic change which comes about. We saw earlier in the lift curve also that the lift was increasing gradually and then it drooped off. This is typically the stall. So, we realized that just having a curved airfoil section or inclining it at an angle of attack with the flow does not guarantee sufficient lift generation. So, the flow needs to remain attached and turn effectively to generate lift. When the pressure increases dramatically on the leeward surface as the flow moves on, we say the adverse pressure gradient is increasing on the upper surface. We will learn more about the adverse pressure gradient later. This is something that challenges the flow all the time, and the flow finds it very difficult to remain attached on the surface if the pressure gradient really becomes adverse. Pressure gradient means the rate at which the pressure is changing as we move along the flow direction, maybe along x, along y, depending on the flow direction. Most importantly, the direction along the body surface. So, when the pressure is on the rise as we move along that surface, it is a case of adverse pressure gradient. Adverse pressure gradient causes flow separation. It also leads to ineffective flow turning due to flow separation, and therefore, the body no longer remains streamlined to the flow, nor does it have the capability of generating sufficient lift with accompanying low drag. Rather, the lift becomes very low and the drag becomes significant, and therefore, it loses its aerodynamic performance. Let us have a brief look at how thrust is generated, because that is one of the four forces which are of major interest to us. We are looking at a very small simplified sketch of an engine here, and it is mounted on the wing of an aircraft, and we are just focusing at that and no other parts of the aircraft. We are looking at the device in a situation where the aircraft is in flight, and the air stream which is coming and meeting the engine gets into the engine because the engine has an intake. So, the front part of the engine allows the air to flow in, that is what is called as an intake or inlet. And then there are many processes which happen in between, which ultimately creates a very high velocity jet from the rear part of the engine. In order to do that, of course, you have to add fuel to the flow and burn it to create this energetic gas, which leaves at high velocity from the end, and it generally leaves from a nozzle. The velocity of the flow which moves into the engine, if we consider it to be V naught, it is coming in at a pressure of P naught, and there is a mass flow rate m naught with a dot on top, because that is a rate, that is a time rate. So, that is the inlet end of the picture. The outlet end, we find the velocity V e at the exit, pressure P e, which may or may not be equal to P naught, and m dot e, the mass flow rate. The m dot e is slightly larger than m dot o, because you are adding fuel. And then we know that V e is much larger than V naught. Why do we need it? We need it because that creates thrust. By the way, this kind of an engine is called as an air breathing engine. It is basically a gas turbine engine, and the one that we have sketched here is representative of a typical turbojet or a turbofan engine. If you have a propeller in front, you could have a turboprop engine. You could think about other air breathing engines too, ones which work at higher cruise velocities like ramjets and scramjets, but we are not getting into all that at this point of time. Neither are we looking at a rocket engine, where usually we do not have air flowing into the engine, but a high velocity jet coming out of the engine, because we have the fuel and the oxidizer in the rocket. It is available inside the rocket, it does not depend on ambient air for it to burn the fuel. Now, the thrust equation looks like this. This is the rate of change of momentum of the gas as it crosses the engine, from which bulk of the thrust is generated. So, it is very important for us to create a high velocity jet, that is primarily responsible for the thrust. There may be some pressure difference between the exit and the inlet end of the engine, but that is usually small. So, the primary reason why thrust is generated is because the engine is able to create a high velocity stream. Now, let us look at a small sketch of the aircraft, which we saw earlier too. This time let us have a little more detailed look at it. So, we have the fuselage, which houses the passengers, the luggage, a lot of equipments, etc. And then on two sides of the fuselage, we find the two wings, which are primarily responsible for generation of lift of the aircraft, and two engines are also mounted on the two wings. They are turbofan engines, incidentally. The wing is fixed to the fuselage at the wing root, and these are the wing tips. You have the right wing and the left wing here. There are shaded portions on the wing. You can see flaps, which are closer to the wing root, and you can see ailerons, which are closer to the wing tip. Also, you see that they occur in pairs. Now, moving to the trailing part of the aircraft, you have a vertical stabilizer or vertical tail. Towards the rear part of that, you have a control surface, which is called rudder. You have horizontal stabilizer or horizontal tail, which are existing as a pair, and in the trailing part you have elevators, which are also in the form of a pair. Now, as is evident, these different surfaces can be controlled by the pilots. They could be tilted, they could be deflected. So, by deflecting these different control surfaces, what the pilot achieves is flow turning. We have looked at the flow turning example in an earlier lecture. We said that lift generation is dependent on turning of the flow. Therefore, the moment you turn the flow, you have the forces and moments changing on the section that you are tilting. So, these different sections can be tilted or deflected, and thereby you could enable flow turning. When flow turning is altered, it generates additional forces and moments, and which can be used to control the orientation of the aircraft with respect to the free stream, and this ultimately helps the aircraft to perform desired maneuvers and consequently control its flight path. Let us look more specifically at some of these control surfaces. The different control surfaces are hinged and are usually located at the trailing edge or rear edge of the wings and the tail, and they can be rotated up or down or to the sides. For example, for the rudder, it is to the sides. Now, the function of a flap is to increase the lift force on the aircraft. Some aircrafts are designed with flaps at the leading edge here, that is the front edge, and we call them slats. The ailerons are control surfaces that control the rolling moment of the airplane around the fuselage. Rolling means it can rotate about this axis, that is what we mean by rolling. How is it achieved? When the left aileron is deflected downward and the right aileron is deflected upward. So, this is downward and the other one is upward. Lift is increased on the left wing, that means this wing. Why is it? Because now the wing looks more like this and there is more flow turning. Therefore, there would be augmented lift on the left wing. And the right aileron, when deflected upwards, will decrease the lift on the right wing, because on the right wing it will be something like this, and therefore, though the main wing section did create a deflection like this, due to the effect of the upward tilted aileron, the net effect of turning will be reduced or maybe like this. Therefore, there is a differential lift created which will create a moment. Of course, as you keep these surfaces further away from the CG, you can create these moments more effectively. And in this case, this will cause the airplane to roll to the right, as indicated by this arrow. The elevators are control surfaces that control the nose up and down pitching moment, that is these surfaces. Nose up and down would be like if you had an axis like this, you are pitching the nose up or you are pitching it down. When the elevator is deflected downward, the lift on the tail is increased, pulling the tail up and the nose of the airplane down. So, the nose would go down, the tail would move up. So, the aircraft will tilt about this axis with a nose down. Similarly, when the elevator is deflected upward, the lift on the tail is decreased, pulling the tail down and the nose of the airplane up. You may have seen an aircraft taking off by deflecting the elevator upward. The rudder is a control surface that can turn the nose of the airplane to the right or left, which is called yawing. So, if you had an axis like this, yawing would be about this axis. That is what is controlled by the rudder. So, the control surfaces, their movements, how they are working in synchronization, in pairs, we discussed in the last 2 slides, and here we are summing up the forces and moments which act on an aircraft with axis and coordinate system. So, you can see over here the 3 forces: lift, drag, side force. These are the aerodynamic forces. Remember that incidentally lift is equal to weight, and thrust is equal to drag in steady level flight, where the weight and the thrust are not having direct aerodynamic roots. We are considering lift, drag and side force for that. Pitching moment, as we said, happens about this axis, which pitches the nose up or down. Rolling moment rolls the aircraft about the x axis, either to the right or to the left, and the yawing moment turns the nose of the aircraft either to the right or to the left, and the associated control surfaces which enable these movements were discussed in the previous slide. So, we conclude this lecture where we revisited the non-dimensional coefficients and dependence of lift and drag forces on angle of attack. We discussed about the basic thrust generation mechanism in an air breathing engine. We discussed about aircraft shape and various control surfaces that it has. Pitching, rolling and yawing moment as well as lift, drag and side forces acting on the aircraft during flight were discussed and were diagrammatically represented. So, with this we conclude this lecture. Thank you.